Brian Wilcox. Brian has been a robotic and spacecraft system engineer at JPL for over 30 years, including 20 years as the supervisor of the Robotic Vehicles Group, which developed the technology basis for not only Sojourner, but also the subsequent Mars rovers. He's also the PI for Athlete, which we just heard about a lot in Scott's presentation, and his interests are in novel mobility and manipulation methods on, above, or below the surface of planetary bodies or moons. Thanks very much.
Okay. Good morning. I wanted to talk to you this morning about sort of the robotic underpinnings of how you might accomplish some of the things that we've heard about. The previous three speakers have talked about the kinds of things you want to be able to do, and then the next question is how do you actually accomplish that? So I kind of like to talk about the three M's, mobility, manipulation, and metrology. Mobility, the issue with 3D construction on other planets is that those things are likely going to be too large to do from a fixed base. So if you have a fixed, an arm or a pair of arms, and they're in a fixed location, they're only going to have a fairly modest reach. And so you're going to want to be able to move that system around and just the way you would with a construction equipment or with a human construction worker, if that worker were not mobile, they would not be very effective because the kinds of things you're going to want to build are large objects initially, not little sort of miniature things. Manipulation, even though you need mobility and you're building large things, you need substantial mobility because you're going to want to do 3D construction. You're going to want to put a material into a three-dimensional position, and then you're going to want to put more material into a different three-dimensional position and so on. And that requires that you be able to move around in 3D and in fact in 6D. That is, you need to maneuver your end effector in roll, pitch, and yaw as well as the XYZ coordinates. So you need to be able to move your end effector, your depositing head, or whatever it is. And lastly, and this is the one that's perhaps most overlooked, is metrology. And that is that you want to be able to measure precisely where you're working, where your end effector is located. And when you're on a mobile base, that's difficult to do. So it's easy to imagine that if you mount an arm to a fixed base and then everything is referenced to that fixed base, that metrology is not very important. But in fact, you're going to have a mobile base, and it's a mobile base in natural terrain where you don't have registration marks and landmarks and other things that give you good metrology. So we're going to talk about the metrology associated with these things. The first comment I'd like to make about robots is that you need to understand a little bit about their kinematics. Now, a robot traditionally has 6 or more links, and you need 6 in order to be able to independently change the X, Y, Z roll, pitch, and yaw of the end effector. So if you're going to have all 6 of those things be variable, then you need 6 motors in order to accomplish that. And those motors traditionally are put at the base of a link, and then you have a rotary motor that rotates that link around a base. Now, years ago, robots back in the 60s and so on, they also had prismatic joints. So sometimes you had a sliding, a telescoping joint. But those have kind of gone away from robotics because of the sealing, lubrication, and cabling issues that go with a telescoping joint. There's a lot of problems with sealing them against the intrusion of foreign material. Lubrication, you tend to expose the lubricant to the environment, and then you try to reel it back in. So there's a lot of reasons why prismatic joints have gone away from most of these modern robotic systems. However, revolute joints tend to have this springiness. And so when you have a revolute joint, it has an axle, it has usually a shaft made out of some hardened material like steel. And that relatively small diameter shaft, even though it's strong enough to accomplish the function, still has quite a bit of wind-up in it. And so when you load the robot arm, it tends to sag a little bit, and even under its own weight, it will sag. And more to the point, when you put an unknown payload on the end, then it can sag in an unpredictable way. And so while a robot can be quite repeatable, it's not necessarily very accurate. And so you distinguish between repeatability and accuracy on a robot. And so if you're going to try to solve this metrology problem, it's not enough to measure accurately the joint angles of the robot, especially the joint angles as determined by the rotation of the rotor in the motor before the gear train, because the gear train winds up by a different amount depending on the output load. And so you need some other method. You either need an output encoder on the other end of the gears, which needs to be very precise. It needs to measure, to a very small fraction of a radian. Or you need some other technique to measure the output. There are other issues that when you design a robot, you often design, two axes to be nominally orthogonal to each other or nominally parallel to each other. But in fact, when you go build it, they never quite are. And so there's a matrix, a coordinate transformation matrix, and in those there are a lot of things that should be nominally zero, but in fact they're not zero. So a lot of elements of that matrix are not zero, and you have to measure those very accurately if you want to do a good job of predicting where that end effector is going to be. And when you have a large robot, these effects are substantial. You can have a multi-centimeter error because you failed to account for the fact that these joints are not parallel or not perpendicular. So one method of dealing with that is a thing called pseudolights. So here's a concept that was produced up at Stanford where you'd take in the Martian environment, you'd put together, you put down some radio beacons, and basically they serve the function. The term pseudolights is a pseudo-satellite. That is, it's like a GPS system. It's a local system that functions like GPS does all over the world. As you know, GPS allows you to get kind of 10 centimeter level precision anywhere in the world, which is a remarkable capability, and yet we don't have anything like that around the moon or around Mars, and it's very unlikely that we'll have those in the near future because those are extremely expensive systems. So the question is, can you build things like that and put them in your workspace on another planetary body? And the answer is yes, of course you can do that. And then the question is what kinds of systems. You can use radio, you can use laser, you can use optics. In our lab we have a thing called Vicon, and Vicon in our case we have 20 cameras, and we put little retroreflector balls on anything that we want to determine the position and orientation of. And the cameras have infrared light sources that are modulated, and so they can look at those with with precision in the camera, and they can basically take the intersection of all the rays. So when it sees a retroreflector ball, it can determine the location, in its image plane, and it transforms that into a ray in space and says that retroreflector is on that ray. And since we have 20 of them, we can triangulate all those and get very precise, kind of least squares estimate of where that ball is. And so you get, it's a commercial system. It's used for motion capture in the movie industry and so on. And you can get very precise knowledge of where anything is in an environment, several times the size of this room to a millimeter or so. So that's the kind of thing that you need to be able to have, and that helps you solve the metrology problem without trying to do it through all these coordinate transforms where you have a transform from some base frame to this robot that has been driving over rough terrain, and well, how do you get the base frame of the robot as measured in the in the absolute coordinate frame of the system? And then once you go from there, how do you account for all the gravity sag and other reasons why an end effector might not go to exactly the right position that you want it to go to? There's another thing called visual servoing, and this is basically what humans do. When you want to thread a needle, you don't have an absolute coordinate system that figures out where the thread is and another absolute coordinate system that determines where the needle is. You just look at the needle, at the hole in the needle, and you look at the end of the thread, and you do everything in relative coordinates. And so that's another great way to do this, is to forget absolute metrology to some degree and do things all in relative coordinates using vision or some similar, may not be vision, human, it may not be, visible light, it might be infrared light or something like that. But basically you would, for example, when a construction site is laid out, the surveyor comes out and puts stakes in the ground. And then the construction crew, they don't work off an absolute metrology system. They work off the strings that are strung between the stakes. And they just look at how close they are to the string. So if they're going to lay down bricks, they just make sure the brick is aligned with the string. And so they do all that by effectively visual servoing. So they just see that, in fact, they've got the brick aligned up next to the string, and now they know that they're meeting the objective of the architect in accomplishing what needed to be done. So you can either put the camera on the end of the end effector, or you can have it just looking over the scene. Oftentimes, like in the thread the needle example, you want to have a camera that's got close-up view, maybe not a very large field of view, but just enough to accomplish the critical part of the work site. Now, if you're going to build something big, one way to do that is with one of these so-called mobile gantries. And so a mobile gantry serves the function of being, having a very large work volume that it can, productively accomplish tasks inside. And so they're used often in this construction, in moving containers, moving ships, things like that. But they have the advantage that they're very efficient structures for carrying loads. So they have a relatively low mass to work volume ratio. And when you think about what is required to take advantage of 3D manufacturing using in-situ resources, you want to not have to bring up very much mass, and yet you want to be able to build a large structure made out of in-situ materials whose mass, you don't really care how big the mass is, because it's all made from in-situ materials. So the ideal way to accomplish that is with something akin to a gantry, a mobile gantry, because that is a very efficient structure. It's relatively low mass compared to its enclosed work volume. So that leads us to Athlete, and Athlete is a concept for making a low mass vehicle. So what it does is it has 6 wheels on 6 legs, and those 6 wheels are smaller than the wheels that you would have for a similar payload vehicle of the same payload capacity. So we had a question, well, what if it gets into soft terrain? Now, soft terrain is exactly the kind of thing why Athlete was built. These relatively small wheels are designed to be big enough not to get bogged down in about 97% of all terrain. Now you say, well, 97, that sounds like a fairly good number, but what about the other 3%? Well, our normal rovers on Mars are designed not to get bogged down in 99.9%, because if you do get bogged down, it's end of mission. If you get stuck, it's end of mission. And of course, Spirit did get stuck, and it was end of mission. And Opportunity got stuck for 6 weeks, and it almost had end of mission. Whereas this vehicle, even though its wheels are half the diameter, half the width, 1/10 the mass of the corresponding wheel actuator that you would find in a more conventional design like Spirit, Opportunity, or Sojourner, Spirit, Opportunity, or Sojourner. These this doesn't have to worry about getting stuck because it's on these legs and it can just walk out. So if it does get stuck, if it does get bogged down, it just walks out. And as a result, you save so much mass on the wheel drive and wheel drive assembly that you pay for the mass of the leg. So even though that leg looks big and looks massive, it is actually not very big and it's not very massive. And that's partly because it's constructed out of this kind of lightweight riveted airframe type construction. As Scott pointed out, we have a capability to to carry a pallet, in this case with a habitat on the side, on the top. And here we're doing a demonstration of extracting ourselves off the top of a lander. So these legs are 3 meters, over 10 feet tall, and allows us to sit on top of a 1/2 scale mock-up. This is a 1/2 scale system, so it's only 10 feet tall instead of 20 feet tall. And it carries a habitat mock-up and is able to lower it to the ground. One of the things that Scott had in his habitability matrix was, that a human really wants to be in a habitat that is level to within a few degrees. And if you've ever pitched your tent on a slope, you find about 2 o'clock in the morning that you really did not want to be on that slope, and you're really sorry that you didn't pay more attention to how level the spot was. Well, if you can imagine that the lander, or that one of the Apollo landers landed on a 12-degree slope. Well, if you had to live in that indefinitely on 12 degrees, you would be very uncomfortable. This gives you the option of bringing that habitat down, making sure that it's absolutely level, and of course also making it so the door is only a few feet off the ground instead of having to climb a 30-foot ladder to get to it. When the Lunar Surface Systems Project came to us and said, well, how do we set down payloads that we are no longer going to use or want to leave in one spot for a long time, we came up with a triathlete concept. 2 of our engineers, one of which is Scott Howe, simultaneously said, well, just cut the hexagonal frame in half into 3 pieces, have the center rectangle be the cargo pallet, and then the other 2, which we dubbed triathletes at that point because they have 3 legs and 3 wheels each, become separable vehicles, and they can go off and grab a different habitat or a different payload and move it around. So the number of athlete vehicles doesn't have to equal the number of habitats. You can have a much smaller number. Typically, the life cycle of a pressure vessel like this is it comes down to the planet's surface as a pantry full of provisions, and then gradually you eat your way through the pantry and it becomes fresh living space, and then eventually you fill it up with garbage and you abandon it on the surface. Okay, so once you have one of these lightweight wheel assemblies on the end of an arm, it can be a general purpose manipulator. So here we pick up an end effector out of a tool holster, and we use that end effector to accomplish a task. And so we can accomplish a variety of non-dexterous tasks. Here we grab a drill, again out of the same drill holster, out of the same tool holster. And you can imagine that if somebody came to you, you were a mission manager, and the customer came and said, I forgot to say, but I want this mission to also drill a 1-meter hole in the ground. You'd go berserk, because if they didn't tell you that at the beginning, how could you possibly arrange your mission to be able to do that? Well, in our case, we would just say, give us your drill, and we'll put it in a tool holster somewhere, and we'll drill a hole in the ground, because we have these general purpose wheels and legs that are able to accomplish all these remarkable things. This is a movie of something that Scott showed a still of, but basically, if you have 2 habitats like this, if you imagine all the precision you need to get 2 pressure doors so tightly sealed that you can open the hatches between them, there's tremendous force because you have 8 or 10 psi across the whole area of the door. So there's a tremendous force pushing these apart once you seal the doors. So you have to get them very accurately aligned, and the way we do that is we have very accurate metrology again. There's metrology, and also force sensing, so that we're able to measure the forces and make sure that we don't have tremendous wedging forces. So every one of these wheels has a force torque sensor in it, which gives you 6 degrees of freedom, you know, roll, pitch, yaw, X, Y, and Z. And so you have all those measurements, which, knowing the mass properties, allows you to measure the forces between the two bodies very accurately without additional force sensing equipment. So you're able to project those forces and torques up to the top, you know, at the door frame and account for those kinds of things. So one thing is these robots, in order to be efficient, we talked about the fact you want to enclose the largest work volume available at the lowest possible mass, because this mass is you're bringing up from Earth, is largely attributable to what compressive struts are able to do. So struts fail in compression. So if you take a business card and squeeze it on end between your fingers, you get what's called Euler buckling. So that's this low frequency. It's, you know, half a sine wave kind of a shape. And then thin shell buckling is when you stomp on a beer can, you know, you get thin shell buckling. So it's a very high frequency. So you have two different types of buckling. This very low frequency buckling of Euler buckling, very high frequency buckling of thin shell buckling. Those have two different formulas associated with them, and an optimal strut is one where those two happen at the exact same load. And so you've designed yourself an optimal strut when you have a strut that though two types of buckling, the onset is at the same point. Then on the end of those tubular struts, you put these rod ends, and you've all seen them. They're a spherical, you know, ball captured inside a cage, and then you have a clevis that squeezes the ball. And what that does is it ensures that the strut is only loaded in pure compression or tension, that you can't apply rotary forces, because if you try to rotate the clevis, you have, at least within a range of motion, the ball just rotates and it doesn't apply anything but pure axial force. So once you have struts that are loaded purely on axis, then the only way they fail is by this kind of buckling. And we did an analysis that showed that the effective compressive strength is only about 3.2% of the tensile strength for these compressive struts. For the range of interest, for the kind of things we're talking about here today, the compressive strength is only about 3.2%. So just remember the number 30. If you had to design something with a tensile strength, a tensile element like a cable, like the Golden Gate Bridge is made out of tensile cables, right? Very strong, very light. But if you have to do that in compression, it's 30 times more mass. So when you have to build something in compression, it's going to be 30 times heavier than if you had the same forces and you're able to use tension cables to accomplish that. Well, now the reason I'm going through all that is that there is a provably optimum lowest mass method for accomplishing the things we're talking about today, and it is called the spider. And it was developed by Jim Albus, the late Jim Albus, at the National Institute of Science and Technology, of Standards and Technology. And basically what it is 6 struts. And again, we have this number 6, right? Because it's X, Y, Z, roll, pitch, and yaw. So you need 6 in order to uniquely define it. So you have a work platform, which is an equilateral triangle, and then 6 struts that are on mobile bases. And then you hang 6 cables from it to have another equilateral triangle. And that work platform can move around in all degrees of freedom. So now you can move that thing in X, Y, Z, roll, pitch, yaw by adjusting the winches that control the length of the cables. And then by driving the base of these things around, you have a purely kinematic system where all the struts are loaded purely in compression. All the cables, of course, are purely in tension because they can't support any other kind of load. And you can move that work platform around, and if you have cameras or other metrology devices, you can measure where everything is, and you know exactly what you have to do in order to make it do what you want. Now what we did is we did an analysis that showed that the athlete system, flexible as it is only about 30% more mass than this, but it has the ability to walk. And so we believe that that 30% penalty is worth it, because now we have elements that can walk. So if you get into soft terrain, you get into very rocky terrain, you have to, put your wheel over an obstacle, something like that, it's better, to have that extra capability that we believe that Athlete offers. So here we have some renderings of Athlete legs that are in fact made out of 6 struts each. So if you have 6 struts, that uniquely determines the XYZ roll, pitch, yaw of the 2 ends with respect to each other. And so you can see how, with exactly 6 struts, you can get, in pure compression, pure tension, you can uniquely determine the forces. For example, if you load it, you can tell exactly which strut is carrying what load and so on. It's completely deterministic. And that allows you to do things that you wouldn't otherwise necessarily be able to do if you didn't have a deterministic system that was where you could compute all the loads in the system. So that led us to do an analysis of what the mass is for different systems. So we took the existing rocker bogie type Mars rovers, which is Sojourner, launched in '96, landed in '97. MER, the 2 MER vehicles were launched in '03 and landed in '04. And then MSL was launched in 2011, landed in 2012. Those 3 line up nicely along our parametric model. And interestingly enough, this is counterintuitive to many people, that the total mass of the system blows up. So what are we plotting here? We're plotting the mobility subsystem mass as a % of the total rover mass. So if you're down around 20%, that's a good thing. That means your vehicle is only 20% of your total mobile mass, which means your payload can be 80%. Well, that's a good thing. 80% payload is great. When the mobile mass gets up around 75%, that leaves you only 25% for payload. And when it hits the rail up there, that means that it's 100% vehicle mass and no payload at all. And you see that the blue line is for Athlete, which uses 4 psi ground contact. That allows you to sink in the softest sand, but that's okay because you can walk out, right? If you get stuck because your wheel is too high a ground pressure, you walk out. You don't try to roll because you can't roll anymore. You're just using it, you lock it, use it as a foot, and you walk out. And so what we see is that with an Athlete type system, you can make a lighter mobility system. You can make a 20% mobility system, and this is for Mars and Mars gravity. And it really pays off when you get to human scale systems. It really doesn't pay off. It's too complicated, too much harness mass, too much motor controller mass and everything, so it crosses over down in here. So for robotic explorers, there's really not much advantage. But as you get to human scale vehicles, 10,000 kilograms, you have a huge, you save roughly half of the mass of your vehicle to make it an Athlete style walking, rolling hybrid vehicle. And similarly in lunar gravity, you find that you have significant payoff. But again, for human scale systems, 10,000 kilos and up, you start to see substantial advantages for using an Athlete style system, which is close to the provably optimum system developed by Jim Albus at NIST. So in summary, the Regolith ISRU 3D printing construction system requires a robot that combines a broad range of mobility, manipulation, and metrology. Now, these are things that you don't usually see combined in terrestrial robots. In normal robot manufacturing, the robot is bolted to the floor, and the metrology is done ahead of time, and there's no need to have outdoor mobility combined with outdoor metrology, nor with manipulation. So most mobile vehicles don't have manipulation. Most metrology is done indoors once ahead of time. And so Athlete is an interesting hybrid of a robot that is near the limit of what is possible to do in terms of mass reduction, both for mobility and manipulation, and to incorporate the metrology needed for 3D manufacturing. Thank you.